Hello everyone, today let's look at Quantipus number 49. This question's pretty cool. It's asking us what's the probability of getting a total of 15 after rolling 5 dice. So imagine these are our 5 dice, and a dice can take values between 1 and 6 obviously, so one valid combination might be we got 6, 6, 1, 1, 1 because this adds up to 15. So notice again that the setup here is just equivalent to solving the equation where each one of these represents the number on the dice. So xi has to be an integer, that's what that means, and all these x's are between 1 and 6 because that's the values that a dice can take. So this is just the classic stars and bars setup with just some additional constraints here. We're basically counting the number of ways to distribute 15 identical dice numbers to 5 dice. And when we have a lower bound on our constraint like this, basically what we can do is just say for these 5 dice, they all have to start with 1 because that's the minimum value a dice can take. So let's distribute 1 of these to every single dice. Now, once we've done that, we essentially have 10 dice values left to distribute to these 5 dice. So here I drew a little diagram. If you don't know the stars and bars method, then do Quantipus 71 first. Basically what we're doing, we have 10 things to distribute to 5 dice. So we're essentially going to draw these lines here and say everything to the left of this line, these are dice dots, the dots on the dice. So dice 1 will get 4 extra dots. This is saying dice 2 will get 1 extra dot. Dice 3 will get 1 extra dot. Dice 4 will get 2 extra dots. And dice 5 will get 2 extra dots as well. So now in this example, our 5 dice would now look like this. This one would add 4, so we'd have 5, and we'd add 1 to here, so we'd have 2, add 1 to here, 2, and then 3 and 3. So this is what one combination of our dice could look like. So what are we doing? It's classic stars and bars, right? We have 4 bars to divide into 5 groups, obviously. And now we can just say we have 14 positions to put things in, 10 plus 4, and we're choosing 4 of them to be our lines. But now notice that one problem with this setup is this example below, because technically we could have chosen these 4 under the stars and bars setup, but this doesn't make any sense because this would mean that dice 1 would have a value of 9, and we know that a dice has to have an upper bound of 6, right, on the number of pips it can have. So essentially, once we calculate this, we have to subtract off all the cases that are invalid in terms of this upper bound. So now let's subtract off all the invalid cases. So how do we do that? Well, let's come back to our 5 dice right here. We have 15 pips or dice values to distribute. So now what would make a combination invalid? Well, it's going to be when one or more of our dice values takes a value greater than 6. So let's just do it out mathematically. Let's define these variables a1 through a6, where ai is going to be the set of solutions where dice I is invalid, and that just means it has a value greater than 6. So that essentially tells us that A1 union A2 all the way up to union A5 is going to be the set of invalid solutions. And now in order to calculate this, we're just going to use basic inclusion-exclusion. So for starters, let's just calculate the magnitude of A1. The magnitude of A1 is just going to be the set of solutions where dice 1 is invalid. So in order to make dice 1 invalid, let's take the smallest possible number that we could give to dice 1 to make it invalid, which is going to be 7, right? 1 greater than its upper bound. Now we also have to give 1 dice to all the others to satisfy the lower bound, obviously. Now in doing so, we've distributed 11 dice values out of 15, which means we have 4 left to give. Now, this is essentially another stars and bars question, right? I need to give out 4 dice values to 5 dice. It takes 4 lines to divide up 5 dice, so I just take 4 plus 4, 8. I'm choosing 4 places to put these lines. So the magnitude of A1, the number of invalid solutions, such that dice 1 is invalid, is going to be 8 choose 4. Now, what's the magnitude of A2? Well, we know it's just going to be the same thing because if I give 7 dice to number 2, we can just calculate it the same way. It's going to be the same for A1, A2, A3, A4, and A5. So the total number of invalid solutions, all these summed up, is going to be 5 times 8 choose 4. Now, when you're doing the inclusion-exclusion, you have to ask yourself, did I overcount anything? And the answer to that question is going to be no, because once I've done the bare minimum to violate the upper bound for 1 dice, I only have 4 pips left to give out. So the most I could give any other pip would be 4 to make this 5, and this is not an invalid solution for A1, right? So there's no overlap between A1, A2, A3, A4, and A5, so we do not need to subtract off any pairwise intersections. So this is the number of invalid solutions. This is our total number of solutions, so let's just subtract this from this. So 14 choose 4 minus 5 times 8 choose 4. So when you use a calculator, 14 choose 4 ends up being 1001, and 8 choose 4 is going to be 70. So 5 times 70 is going to be 350. So let's just subtract 350 from 1001. So this answer is going to end up being 651, which is the number of valid solutions that satisfy this constraint. But how many total ways are there to roll 5 dice? Well, any dice can take 6 values. The second dice could take 6 as well. So it's just going to be 6 times 6 times 6 times 6 times 6, 6 to the 5th, which is going to end up equaling 7776. This is the number of ways we can sum to 15. This is the total number of ways we can roll 5 dice. So therefore, our probability is going to end up being 651 over 7776. That's the final answer.